one of the things I wanted to talk about was sort of trying to make some progress on exactly some of these questions about trying to avoid having to calibrate our proxies to get a transfer between our climate state variables and what's measured in the paleoclimate records. I think my increasing mantra is that, particularly O18, but several other quantities we measure in proxy archives, they're not actually proxies, they're just climate variables that you don't typically measure from a weather station, so we call them proxies. But O18, for instance, is a perfectly climate variable, which we can model, so that's quite helpful. Just up front, I want to recognize in particular Caleb, who's done most of the number crunching on putting together this material. I also wanted to recognize Sam and Jesse Nussbaumer, and also Tony Wong as well, for giving us some output from the coupled version of the isotopic CESM that we've used to drive this. They were really instrumental in actually finally assembling the model, which is great, as well as the crew of the LMR. I guess it's, yeah. So way back in the past, back in probably 2013, we were standing here. We saw in front of us a pathway surrounded by this luscious vegetation. We thought, well, this is clearly the path to enlightenment. And so we had these, this sort of naive approach, perhaps, where this actually came up a little faster than I'd anticipated, because I have some more humorous comments, so we'll get rid of that. So we had this idea, there's a pathway here to enlightenment, and it all worked pretty well. We had this idea, we had the pieces, we just need to assemble them, and with a certain degree of adolescent humor, perhaps, there we are, we can start thinking of different components that were really necessary to get us to this point of enlightenment. We needed to know, have our relevant data set, we needed to how to treat them. I would say Julian has the only particularly humorous picture when you Google his name, you get this picture. So and I guess similarly, Eric here has a somewhat of a more scowling face on his when you Google his images. Sure. So we had this great idea that we can assemble these pieces, we have data, we have a framework, we can treat our uncertainties, we get to climate, and we're using proxy models. This is all great. So we're all set to move forwards to our point of enlightenment, which had something to do with understanding climate variability over the last 1,000 years. So really I want to pose two problems which I'm going to show you progress on. I think it's sort of comes along the same comment I noticed Greg made earlier, that we have promise here, but we haven't quite reached our point of enlightenment. So I'll come back to talk about that at the end as well. When we're starting to think about replacing our proxy system models with actually physically based or mechanistically based models rather than statistical regressions in some form or simple models, I think you can have more complicated statistical models which pretty much get you there, but I guess I'm really talking about linear correlations with temperature for the most part. We have a couple of fundamental issues with sort of what we had published as the LMR 1 or LMR 0, one of which, a criticism which I ended up being convinced is not a problem, but I want to give it as a problem to begin with, that by calibrating our proxy information with temperature, somehow perhaps we're building in the answer, we're building in a global warming trend simply because we're calibrating. That's not true, and that can be shown statistically. But there is this sense that once we go through calibration in any form, we open ourselves up to this reliance on data. Whereas if we can build models based on first principles, we can bypass this entirely. Now that's, of course, not to say that first principles models are without calibration. So there is we've sort of just pushed this, this issue under the rug a little bit deeper, but it's still there. The other problem is that by making simple regression relationships, we're making the case that our proxy or our climate variable is only related to the thing that we're regressing. So it's temperature, for instance. And of course, when we do these sorts of correlations, the regression is not, well, the correlation is not 1. It's something far less than 1. So there's additional information that we could presumably extract. Maybe we could use a multivariate regression and get a little bit more of that information. Or maybe we could use some clever nonlinear model, perhaps some physically based model. Again, we can extract more information. So that's perhaps our two motivating reasons here. There's a big blank gap down the bottom here, and that's the other hand, and that is by having increasingly complex models, we start with very simple models and we go to more complex models. We're getting better physics, chemistry, biology, but we're also probably introducing additional sources of error. So we have a competition. Do we want to have better models that better capture the physics that probably have complicated errors? Or do we want to have a simple model that probably misses a lot of physical relationships but has a set of errors that are maybe easy to understand? There's somewhat of a trade-off there. And I think what I'm presenting today is essentially one extreme. What we've been hearing, particularly from our first version of the LMR, was the other extreme. And there's a happy middle ground in the middle, which is lurking somewhere around our candidate, I think, for what we're putting forward for release. So that click is out of order, but don't look at it yet. So the sort of the basic notion of using proxy system models or models that transfer climate information into observable quantities, it was laid out by several people, I suppose, but Mike Evans, I guess, really put forward this notion that we have our climate, we have something that senses climate and archiving process. Maybe this is formation of corals, for instance. All of these things can be represented inside a climate model, a GCM. So we don't really have to necessarily treat these as separate components. Arguably, we could treat these inside our climate model and simply go directly to our observations from climate model output. And there's a couple of examples here. I would say specifically the isotope ratios related to the hydrologic cycle are a good example of that. We don't need to build a model that translates temperature into isotopes and then build up, say, corals, and then we archive that somehow. Those processes can be modeled within a GCM. And so that kind of becomes convenient. There's 3 examples of that, which I'm specifically aiming for, so I'll show you those in a moment. So yeah, we can rely on using the GCM to actually do a lot of our translation between other climate variables like temperature, moisture, winds, and so on, directly to our observable quantities, isotope ratios, tree ring width, and so on. And again, I really want to put this forward as a conjecture, and I'm going to argue that we sort of make half progress on this. This is actually not a done deal, I don't think. The idea here is that by doing this and having a mechanistic understanding, particularly with regard to tree rings, which is one of the set of proxies we're using, that we can extract more information from tree rings by using a physically based model. How we actually do that essentially is it better accounting for the growing season and water and temperature stresses during the growing season, as well as light limitations on the vegetation. These sorts of things are built into models like VS Light or VS for that matter, as well as other carbon cycle models that exist, physiological models. So too with ice cores, I think we can make the argument. Yes? Yes, I do. It's humming on the microphone. I'll stick it over there. I think we can also make the case for ice cores in particular that it's very well known that ice cores, isotope ratios correlate with temperature, but they fundamentally are not temperature records. They're hydrologic records, and part of the hydrology is related to temperature. So there's a translation there. So we should be able to do a little bit better with isotopes in ice cores if we're simulating the isotopes rather than just the temperature component. I think in terms of our third proxy we're going to focus on is corals. I think we're likely to see limited advantages. We've already heard that corals are very nicely correlated with temperature, sea surface temperatures, and only in some cases is the seawater O18 a dominant component and perhaps somewhat a minor component for many sites. So by going to a physically based model, we might be looking for a more limited advantage there for corals. So in the setup that I want to present results on, we're using these 3 proxies where we're using the simulated O18 and deuterium, actually O18 only, of annual precip from a GCM, the isotopic version of the NCAR model. For corals, we're using the seawater plus a temperature scaler based on the simulated temperature. We use that as a constant value, which is a critical point, and it's one that is going to deserve attention. We use a value of minus 0.21, which is sort of a characteristic representative value. But you can imagine not every coral behaves that way. So if you assume it does, our model is losing information somewhere. Then final for tree rings, we actually use the normalized GPP, the gross primary production, that's explicitly simulated by the model. It's related to photosynthesis, and within the NCAR model, there is a calculation of photosynthesis that uses sort of a physiological approach to look at light, temperature, and water limitations. I will note that Professor Andrzejkaitis mentioned last week that there's no known observation that shows correlation between tree ring width and photosynthesis rates, which I think is fine. Really, what we're doing here is we're picking up the growing season and the temperature dependence of the growing season, to a most part, actually, I think. Okay, so we have 4 experiments I'd like to describe. Within an LMR framework, we're assimilating this set of proxies that we've heard about into 2 different models. One is CAM, the atmospheric component of the NCAR model, which has been forced with observed sea surface temperatures. We also use CESM, which is coupled, so it's free running with respect to temperatures. Both of these models have isotope ratios and photosynthesis in them, which is our direct proxy simulation. And then we have 2 varieties of each of these, one in which we're using just linear regression with temperature for our proxy model, and the other one where we have our mechanistic process model. We have this little matrix of 2 by 2, 2 models, 2 different types of ways of treating the data. And what we're shooting for is the ideal case where we have mechanistic models in a fully coupled model, and this is our ideal perfect outcome, and this is kind of our null hypothesis in a way with our linear model. So let's have a look at, see how we do, and you should immediately gather from the fact this is a presentation that we do pretty well. If we did lousy, I wouldn't be presenting anything. I'd be presenting a sad story or something like that. So this is actually mapping up with those same set of 4. We have CAM as the prior on the top, CESM, which is the coupled model, the prior at the bottom. And then on the left-hand side, we've got the correlation coefficient. And on the right-hand side is CE. If we focus on the correlation coefficient for a moment, when we use the linear proxy models, we get a distribution of correlation coefficients at each location where we verify the proxies. Our verification is done by bootstrapping, where we withhold some proxies, do the assimilation, and verify against the withheld ones. We withhold 20%. We do that 5 times, so everybody gets a turn to be included and excluded. What we see is if we use the linear correlations, we get a relatively modest correlation, whereas when we use our physically based model, we get generally higher correlations, and that does pretty well. When we use CESM, we see broadly a similar sort of result. Even with the coupled model, we're seeing this advantage. Now those who, and I guess I should say, I like correlations because I understand them well. The CE I understand less well, but we see similar advantages there, which is telling us something about we're getting both the mean structure, the mean variance right, but also the amplitude of the variance a little bit better as well. There are a couple of things that you should note from this. One is that our null case, where we're using linear models, actually appears distinctively worse than what we had published. The reason for that is because what we initially published, we had screened the data, which is the data that was available for only temperature-sensitive proxies. So we'd already screened the data, and we didn't do that. Right, okay. What we do have, the other point I wanted to mention is we actually have a much larger data set, which probably has a lot more records, particularly the tree records, that have a larger component of moisture dependence. So maybe we're losing our correlation there relative to what we did have through those additional data. We have to treat the new data more reasonably to really extract the information from it. So overall, we're doing quite well. This is looking really encouraging. What I don't have is maps. I'm not going to show you maps that match this, but similar to the maps of verification that Greg showed, we're actually showing great improvements, particularly over North America, where there's a lot of trees, which is quite good. When we start looking at this by proxy type, on the left is corals, in the middle is tree rings, on the right-hand side is the ice cores. We're seeing most of the advantages actually coming from the tree ring. And this is, again, really coming from we're now starting to include a sensor model where we're picking up information at the time the trees are growing, and we're doing that through the photosynthesis. The trees are only growing during the growing season, and that's when our proxy is sensitive. So rather than choosing a time of year when we're going to develop our regressional relationships, we're letting the physics and the biophysics of photosynthesis capture that for us. Interestingly, the correlations with, the verification correlations with corals doesn't really show a great deal of advantage in using a physically based proxy system model. And I think this is largely coming from the fact that, for the most part, the seawater contribution to the coral signal is much more modest than the temperature component. So we're doing already pretty well with just the temperature correlation at many sites. And you can see there's little wings where there's clear differences from that too. The ice cores are also somewhat of a mystery to me and a little bit problematic, I think, actually. I was hoping to see really big advantages here, and that's actually not what we see. We don't see clear advantages of going to a process-based model. The reason for this is unclear to me, and I'm going to make some suggestions in a moment. But again, most of the advantages we're seeing here is actually coming from the tree rings, which is something we've already heard. When we look at this in map sense, what we're looking at here is the change in CE as we go from our, it's a difference of the improved mechanistic proxy system models minus the CE when we use our linear model. So it's an improvement in CE as a difference. So we're seeing generally places where we have our trees, in fact where there are the tree records, that's where we're seeing the advantages. But interestingly, where we see the coral records in the diamonds, we're actually seeing really quite modest, if not more poor performance in some cases. Similarly, the ice core records aren't performing particularly well. So a couple of summary points from this. One aspect that we have to deal with when including data in this type of format is accounting directly for the uncertainty of all our proxies. We have to know how accurately or how what's the error on each of our proxy quantities. So the error itself captures several things. The analytic error, the actual error you would get when you run the sample on your mass spectrometer is tiny, and that's actually not the relative error. For instance, for O18, I know well we can get O18 to 0.015 per mil. That is not the error that we care about. That's basically nothing. It's these other three which are important. There's the representation error. To what degree does the proxy record that I record represent the climate variable, in this case a grid average O18, for instance, from the GCM? How representative is that coral of the quantity I'm trying to reconstruct? And then there's two other errors associated with model error. One is related to the fact that the equations we have in a GCM are approximate equations. They're not the perfect equations of atmospheric properties. That's probably a large source of error. The other one is that even if we did have the correct equations, the full equations in the model, the parameters we choose for those equations are also probably not accurate. So there's large errors associated with these. These are actually really difficult to evaluate and identify. So what we've done in this case, we've used an approach where we've said we want to set up our error such that once we do our assimilation, the mean assimilation error, the error from the ensemble average in the assimilation, that the magnitude of that mean error is equally as large as the ensemble spread. So we're balancing the magnitude of our error relative to the ensemble mean relative to the spread of our ensemble. And often this is referred to as a calibration ratio, where one would take that guy divided by that guy, essentially, and be 1. We've put this in as a requirement and said, okay, to obtain this, what is the uncertainty we have on our proxy quantities? And that gives us, for each of our proxy records, a total uncertainty measure, a total error that we can use. By doing that, we are treating all our proxies equally and fairly. Turns out by this mechanism, some proxies have very little information. They have huge errors, so they don't contribute to the assimilation well. But other records that ultimately have small errors are very influential in the record, influential in the assimilation, as they well should be. But this is a choice. It's arguably a subjective choice, but it's a relatively objective subjective choice. Relatively honest one. So let's have a look at actually how some of the reconstruction works. On the left, this is our worst case scenario, perhaps, where we have our linear models. And we can see here we're plotting from 1880 to the year 2000, the global average temperature anomaly with 0 in the middle, 0.4 there, and positive 0.4 there, minus 0.4 there. Black is the LMR, several other verification data sets for global mean temperature as well. And on the right-hand side, we see the version where we use our mechanistic models. So there's a couple of things to note here. One is we actually get higher correlation. So our correlation coefficient has increased a little bit. We get 0.36. So that seems to be advantageous. We do have somewhat lower variance, which I think actually makes sense to me. And I'm not sure if this is actually the case, but because, for instance, we're choosing a constant value for our temperature scalar for corals, and we're not fitting to the temperature record, the 0.21 we use is probably generally lower than you would get through a fit. So we're probably losing some amplitude in that sense. The other thing which is a little distressing actually is our trend by doing it this way is actually weaker. We're getting a global warming type trend of only 0.28 Kelvin per century relative to this other case where we've used calibrated against the observations where we get 0.73, which is much closer to the consensus view of all the other cases. So there are some advantages, particularly with correlation, but there are also some disadvantages. We're giving something up by going this route as well. I did want to come back to sort of a general point here that by going to the mechanistic models, there's really two advantages. One of which is this sort of, we're getting away from the calibration in some ways, but the other is that we do know our proxies depend on many things. They don't just depend on surface temperature. In particular, O18 precipitation depends on the large-scale circulation patterns. We can see that. So what we should be gaining is more information about things like circulation, and we're giving up some of the advantages that we had perhaps for surface temperature. So to illustrate that idea, I wanted to go back to this archaeological result from the turn of the century. What we're looking at on the left-hand side is a model simulation of the leading principal component of southern hemisphere geopotential height at 500 hectopascals. This is often referred to as the southern annular mode, where there's generally a mode with low pressure over Antarctica, higher pressure somewhere in the subtropics. On the right-hand side is the corresponding map, or regression map, of O18 and precipitation, where we see sort of synchronously a high isotope anomaly around the Southern Ocean and a low anomaly over Antarctica. So very crudely, the approach here, I guess Sandy referred to these earlier as iso something. Oh, it was Bronwyn. Isomodes. Then you had an ENSO isomode that's somewhat characteristically similar. So one of the ideas here that if you have enough isotopic information from around Antarctica, for instance, you'd be able to take that information, invert it to get the circulation pattern. So let's see how this works for the LMR. This is, once we have these reconstructions from our physically based PSMs, this is the leading mode of variability in geopotential height for the southern hemisphere on the left and then the northern hemisphere on the right. And we see a couple of things. One is it certainly does reproduce a pattern that's similar to that earlier model from 20 years ago. The pattern here shows an out-of-phase relationship between the Southern Ocean and then the region over Antarctica. This area here in sort of the Bellingshausen Sea is quite well known to be correlated with ENSO. That I guess Eric and others have done quite a lot of work on that in particular. The lower panel here shows the time series of this variation. It's important to note a couple of things. One is this pattern in a very slightly different form appears in the prior. If you go looking for this thing in the prior, yep, it's in there and it kind of looks like that. However, the prior of the time series that matches is 0. There's no variability in the time series in a statistical sense. This is one ensemble, realization, but we do see there is some sort of low frequency variability as well as year-to-year variability. I suspect with many realizations that individual variability will vanish, but some of the low frequency components will come out, and that part is coming from the proxies. Similarly, if we look in the northern hemisphere, I always have to orient myself a little bit for the northern hemisphere, where we see Greenland is in there, North America's over here, we have Scandinavia down to Europe there. We start to see a pattern that's not really like the NAO, which might be one way of thinking about the leading mode of variability. But in fact, we see a Pacific anomaly that's more like a Pacific North American pattern that's also well known to correlate with ENSO variability. Once again, we see a time series, which if we were just using the prior, there would be nothing statistically different from 0. We start to see a little bit of low frequency variability, which again, we'll have to look at more carefully to see if it holds up to a number of ensembles. But we should be starting to see some of this variability, if it's truly in there, as represented by the proxy. So I wanted to finish with just a couple of things that are related. One of the major advantages we have is here I'm just showing the last 150 years, essentially the instrumental period. One of the great advantages of using physically based proxy models is we can be a little bit more robust in our verification as well. We can verify against the proxy quantity. We're looking at the error in O18 that's simulated rather than the error in temperature that's inferred from the O18. We can do our verification in observation space rather than our verification in a reconstruction of temperature space. What we're looking at here again, using CAM as a prior on the top, CSM as the prior on the bottom, and the result that I showed earlier is actually replicated back in time here, 1850 to 2000. We see an advantage in the correlation for CESM here. We also see that in the earlier period, 1500 to 1850, and when we don't have many records, we still see a general advantage there. And again, what we're doing here is we're looking at the correlation between the actual measured, say, O18 in coral versus the simulated O18 in coral. So it's a fair observation to model quantity comparison. And we can do that directly by using these proxy system models, mechanistic models. Again, the key here is that we can do a more robust validation so we have a better idea of our uncertainty. It is different from the constraint problem. Let's see. I'm going to jump over that one. So a couple of key points. First of all, the way we've gone about this is we've used our three main proxy types as our targets. We've seen improvements with tree rings. We've used a GPP simulation that's physiologically based, but really what that's doing is it's telling us that we're getting growing during the growing season and there's water stress on vegetation, not just temperature. So we're getting an advantage that way. We only see really modest improvements by using seawater as an additional factor for corals. Maybe that's because we've got other errors that we need to work on before this becomes the most important error. And I think one of the big areas to work on is to understand why we're not getting more skill when we're doing our simulations of O18 in coral, in ice cores, using our ice cores as a forward modeling our ice cores. I think there's a couple of reasons that might be due to. One is that we do know year to year the correlation between temperature and O18 of ice cores is not particularly strong. It's lower frequency 5-year averages that do a little bit better. So if we do our validation for the low frequency, it might still come out quite well. So at this point, we come back to our bridge. We now have a different bridge. You'll notice there's now no enlightenment at the other end. It's a little bit white at the end of the tunnel, which I suppose is good. What we do have, though, is a different bridge. We've got much sturdier scaffolding. So we know a lot of things about this problem. We've made a lot of progress. And I'd say we actually have made progress on this search for enlightenment or something like that. But we also know a lot more about our methods, where our problems lie, and where the advantages will lie in the future as well. So I think with that, our illustrious leader there is still pointing out that there is a way forward, and it's just down this train track. What could possibly go wrong? So that, I'll stop. Thanks. Yes, sir.